Okay, welcome back once again. Chemistry 3202 course overview review. What we're looking at this time is Unit 1, Section 3, Lesson 3, Predicting Shifts, Q versus K. This material, Q versus K, is dealt with on page 517 to 520 of your textbook, and we're also going to do another little analysis of the effects of temperature on K, just a little review. And as well, we have some homework questions here that apply to the material that we're going to look at today. Okay, what we're looking at today, predicting shifts in balance. So here we got a little diagram of this zebra out on the Serengeti being chased by this lion. Okay, now all of a sudden we give the zebra a Kawasaki motorcycle, and we know that somehow that's a stress on this system, and we're going to upset the environment here. The system is going to be upsetted, but we wanted to be able to figure out, well, what is going to be the effect of this stress? Can we predict this numerically as to what will happen to the system when we stress it? Okay. Up to this point, we've been dealing with Le Chatelier's principle from a qualitative perspective. We could say, well, the color is going to change one way or the other, or we're going to see an increase or decrease in pressure or increase and decrease in temperature. But what we want to do now is quantify the effect to be able to predict the way the system will shift. Okay, here we go. So a quick overview here. We said up to this point, Le Chatelier's principle states that an equilibrium will be responding to an effect or a stress to counteract the stress such that we would change the concentration, pressure, and or temperature. And we said no matter what happens here, K is a constant. It stays the same. The value of K stays the same when we change concentration or pressure. All that's going to happen, of course, is the system is going to try to respond. And we looked at this last day and we said, okay, if we had a little graph here and we had two systems that were, okay, a blue and a red, and all of a sudden we stress this system by removing some of the red reactant, then we would get a new balance achieved here, and of course this guy would drop or go up accordingly. So we're saying that Le Chatelier's principle suggests that we're going to get some kind of shift in order to counteract that change. So we would see that graphically there. Some things that do not affect equilibrium, no matter how much we change them, right? Remember, if we add a catalyst to the reaction vessel, the only thing the catalyst does is it reduces the amount of time here that we would readjust. So this readjustment time is reduced because we're reducing the time it takes to get to the forward reaction, and the forward reaction equals the reverse reaction. So we're reducing the time it takes to get to the new equilibrium. So the catalyst has no effect on where this is going to end up. It just reduces the time it takes to get there. So no effect on the position of equilibrium. We also said if we start changing the surface area of solid species, it has no effect on the position. And again, pure solids, pure liquids, their concentrations cannot change. Therefore, you can do what you want with the pure solids and pure liquids. It's not going to affect the position of equilibrium. And again, if we just increase the surface area, all we're going to do is make the collisions much more quicker, and therefore we would reduce this time period of adjustment here. All right, so the surface area would be similar to what the catalyst would be doing. Okay, and of course, if the opposite sides of the equation have the equal number of moles of gases, then obviously there's no advantage to shifting. So that's three things that do not affect equilibrium. There we go. And another little recap here, we said if equilibrium constants are temperature dependent, they'll stay at a constant value providing the temperature stays constant. If we start fooling around with the temperature, making it hotter or colder, then the value or size of K is going to change accordingly depending on whether the reaction is endothermic or exothermic. So temperature and K are dependent, right? If temperature fluctuates, then K is going to change accordingly. So let's look at this Q versus K. What is it we're talking about when we refer to Q? Well, Q refers to a reaction quotient. And it's basically the same as the equilibrium expression K, except K is based on equilibrium values. Q is going to be based on the initial concentrations that we put in a container. So what we want to do is we're going to look at this and say, before anything happens, look at the concentrations. Maybe, just maybe, we're already at equilibrium. If we are, then perfect. No shift is necessary. But if we put in some initial values and it doesn't equal the K value, then we're going to say, oh, we're not in a state of balance here yet because Q does not equal K. So this is the point of calculating what's called a Q. All right, and if we compare that to K, K is based on the equilibrium values that we would get from an ice table. So Q is based on initial values, K is based on equilibrium values. All right, and we would get the equilibrium values from the ice table. So we want to look at the three comparisons here. You know, what happens when we put our values in? And I'm going to do a calculation for you now in a second. That'll make this a little more clear. We got three situations that can come up. If we put the initial concentrations in and they end up equaling K, we'll say, hey, we're already at equilibrium. No stress. We're already in a state of balance. Everything is where it should be. Everyone's in their happy place. The forward rate equals the reverse rate. The concentrations are balanced out. They're not going to change anymore. So that's that situation when Q is equal to K. So what happens if we put our values in and Q ends up being less than K? Well, what this is saying now is that the concentrations are no longer in a state of balance. We have some kind of stress induced here. And what we're saying then is that if the value of Q is based on the initial concentrations of the products and reactants, and Q ends up being very small, in other words, what we're saying is if the products are smaller than the reactants, so I'm just going to use, say the products have a concentration of 1 and the reactants have a concentration of 10, this is going to end up being a value that's going to be a smaller value than K. And what we're looking at here is we're saying the products are way too small. The only way we can start to get the products bigger is if we shift forward. Okay, so if Q is too small, we need to make it bigger because we want it to equal K. And what we have to do is we have to shift in a direction that's going to make the products bigger. So therefore, we're going to have to shift forward. So if Q ends up being smaller than K, we need to shift forward to increase the product size, and then that would increase the value of Q. All right. If we end up seeing the other scenario here, where Q is greater than K, what we're saying in this case is that the value of Q is too big. We need to make it smaller. So what's happening here, we can say that if it's products over reactants, now our product concentration is way too big. The products are way too big. How are we going to make Q smaller? Well, we can make Q smaller by reducing the amount of product. In other words, we're going to shift to produce more reactants. We want the products to go down, the reactants to go up in order to get Q smaller. Let me give you an example to show you what I'm talking about. Here's a question from page 517 of your textbook. It's saying the value for K for this particular reaction is 280. Okay, so K is 280 at 1,000 kelvins. What we're going to do here now is we're going to take a 1 liter flask and we're going to put in 0.068 moles of sulfur dioxide, 0.38 moles of oxygen, and 0.098 moles of sulfur trioxide. What we want to know is, are those values the equilibrium values? Like, are those concentrations the stable ones? So we'll say, okay, fine. We're not going to do an ice table or anything like that because remember, Q is based on initial concentrations. We're only trying to figure out if we're at equilibrium. So no ice tables required since Q is based on the initial concentrations. Okay, we go about it the same way. Q is products over reactants, so SO3 squared divided by SO2 squared times O2. And again, we would only include gases or aqueous solutions. We put our values in that we were given, the initial values, and lo and behold, the answer works out to be 5.47. So we're looking at this and we're saying, are we at equilibrium? And the answer to that should be no. If we were at equilibrium, we should get 280 for our answer. We don't. We get 5.47. So Q is not equal to K, therefore we are not at equilibrium. The question would be then, okay, let's see if we can get to equilibrium, which way do we have to shift? Now let's look at it. Q is way too small. How do we get Q bigger? Well, we get Q bigger by making this top number bigger. So SO3 has to get larger. These guys have to get smaller. So if I want Q to be bigger, I want Q to be 280, I'm going to have to shift forward. Okay? There we go. So since Q is less than K, Q is too small, it has to shift forward. We have to try and make more product. And in order to get Q larger, of course, we need to get the products larger, so we're going to shift forward. And that's what we're looking at. So we're looking at this numerically, and we can say, yeah, we have to shift forward. We have to shift forward quite a bit in order to get that to be 280. All right, so the only purpose of Q then is simply to determine if we're at equilibrium and then to be able to say exactly which way the shift is going to be. And that's the purpose of Q. Okay, here's another type of reaction. In this particular one, it's saying, okay, we're going to take this system, 2 nitrogen dioxide is in equilibrium with N2O4, and it says we've got a movable cylinder with a piston here, and we've got this 0.0206 moles per liter of NO2 and 0.0724 moles per liter of N2O4. And it says that we're at the equilibrium. So the equilibrium concentrations are given. So now that we know equilibrium concentrations, we want to be able to calculate K. All right, not a problem. K is going to be products over reactants. So therefore it's going to be N2O4 divided by NO2 squared. We put our equilibrium values in, and we get 170.6. So again, K is based on equilibrium values. In part B, it's saying, all right, what's going to happen to the system if we take this movable cylinder and we make the volume of the container half? So we got this piston, and we're going to push it in the cylinder halfway down so that we've reduced the volume by 1/2. So in other words, we went from 1 liter, say, to 0.5 liters. So what we're going to do here is we're going to say, all right, the very first thing we have to do is calculate the new concentrations. Okay, so the concentration of the NO2, we're going to say, assuming it was 1 liter and we put it in half, so we got 0.026 moles per liter, but now we only got half a liter. So that's the new concentration of NO2. We would also do this for the other reactant, or the other product, sorry, C equals N over V for N2O4. And again, we've got 0.0724 moles per liter, but we only got 0.5 of a liter. So the concentration of this guy increases by 0.1448. Okay? So what we're seeing here, because we have an increase in pressure, remember Boyle's law? Boyle's law said if we reduce the volume, we're going to increase the pressure. So if we looked at this from a Le Chatelier's principle perspective, because we've increased the pressure, we're going to shift to the side with fewer moles of gas, which means we should shift forward. All right, let's see what the Q has to say about this. So now that we have some new concentrations, we have a new situation here. The initial situation now has changed because we've introduced a stress. We've increased the pressure, we've decreased the volume. So now we have to get a readjustment. There's a period of readjustment, and now we want to know what the new balance is going to be. So based on these new numbers here now, we're saying, are these new numbers equilibrium numbers? And the answer to that would be yes. If we can put the numbers in this equation up here and it equals 170, then these would be equilibrium values. If they're not, then we're not at equilibrium. So in C, we're saying calculate Q. All right, well, Q again is products over reactants, just like it was up above, but it's based on these new values. Okay, so again, it's N2O4 divided by NO2 squared. And when we put our new values in, lo and behold, we see that the answer works out to be 85.3. Are these new values equilibrium values? Absolutely not. These are the values under stress. So the system now has to somehow shift in order to get these values down to a level where the equilibrium constant is going to be 170.6. Okay? So we're no longer at equilibrium as a result of this stress. So the question would be then, all right, well, if we're not at equilibrium, we're under stress, which way do we have to shift to get to equilibrium? And we're saying here that since Q is less than K, Q is too small now, Q is too small, we need to somehow shift in order to get Q bigger, so we're going to try and get the products bigger. So we need more N2O4. So we're going to shift to this side to make more N2O4. And there we go. Okay, the value of K does not change because K is a constant. What's changing, of course, is the concentrations are trying to get this new sense of balance here, and therefore we would expect this shift forward. Is this what we predicted over here? We predicted based on Le Chatelier's principle, the qualitative aspects. We said since we're increasing the pressure, we need to shift to the side with fewer moles of gas? Absolutely. That's what we predicted. Our numbers prove it. Okay, and finally another little quick review here on the effect of K and temperature. All right, we said the value of K is temperature dependent. That's very important. Don't forget that. This is the only time that K will change. In the last example, yeah, we started stressing the system by changing the pressure and the volume and all that, but K stayed to be 170. It did not change. Everything else had to change to try and reach the equilibrium constant. In this case, when we change temperature, everything changes here now. The concentrations are probably going to have to change. The size of K is going to change because of the effects of temperature. And the idea being here, of course, is that if the temperature change causes the system to shift forward, then that's going to result in the increased products, which means K is going to go up. If the change in temperature caused the system to shift backwards or in reverse, then that's going to cause the products to go down and K will drop. Only when we have a temperature change. Okay, any other time when the products or reactants change their values, then they're changing their values to try and reach or get to that equilibrium number. So this is the only situation. This is what we mean by K is temperature dependent. K will change if temperature changes. Okay, so for this example that's given, if we increase the energy to say 300 kilojoules, that's going to cause this reaction to shift forward. As a result, the products are going to go up, and therefore the value of K will go up. So that's going to increase the products, which means we're going to increase the value of K, only because of temperature. All right, that's the end of this one. And make sure now you take advantage of our online tutor and the online content that we have. And don't forget, if you have any questions on this you want answered, just drop a few questions in the discussions, and I'll try to answer them for the next session. Okay, see you later.